All right, boys. Hope everyone's doing all right. In this video, I'm going to introduce you to two different derivative rules. They're structural rules. But before that, let's just recall those basic rules we have so far. One is the coefficient rule, which says the derivative with respect to x of any constant is 0. Different than the derivative of the coefficient rule, 4 times a function, or 3 times a function, or 18 times a function, in which case we pull out the coefficient times the derivative of y, which we can either call dy, dx, or y prime. Okay? Constant rule, coefficient rule. We have the sum difference rule, which says the derivative of a function plus or minus another function, x squared plus sine of x, 4x cubed minus square root of x, is equal to really the derivative of the first function plus or minus whatever the sign is, the derivative of the second one. Okay? In other words, derivatives quote unquote distribute over addition and subtraction. And we also have the good old power rule, which says the derivative of x cubed or x squared or x to the 1/2 or x to the 3/5 is, you guessed it, n, the power of n comes down, and then I knock the prior power down 1. Okay? So those are the basic rules we have established so far. Okay? Now we're going to add two more rules, and they kind of play off of the sum difference rule, but they're a little surprising. Again, all of these can be verified with the limit definition. That's where they come from, directly or otherwise. Okay? If I want to derive, this is called the product rule. If I want to derive two functions, both of which contain an x, okay, so one of them is not a coefficient, right? It's not 3 times sine of x. It's not 4 times x squared. Okay, if both f and g are both functions that contain an x, not constant functions, then what the product rule says, this is a little surprising, is we take the derivative of f times regular g plus the derivative of g times f. And a lot of times guys remember this as fig gif. That's a little way to remember this. F prime g, that's kind of the fig part, plus g prime f, that's the gif part. Okay? So that's what's called the product rule. The quotient rule, which is also unexpected, tells us how to derive the ratio of two x-containing functions. So again, f and g aren't just constants, otherwise I would call those coefficients. Right? If it were 3 divided by a function, that 3 would be a coefficient. Or if the 3 were g, it would be 1/3 times a function, which would make it a coefficient. But let's assume that f and g both are functions of x. In which case, and this is surprising too, the derivative of the ratio of two functions, both of which contain an x, is going to be g f prime minus f g prime all over g squared. Okay, and the way I remember that back in the day, if f is high and g is low, numerator is the high, g, the denominator is low, then I remember this as low, that's g, and f prime would be d, the derivative of high. Low d high. All right, minus f, that's our high, d low, that's a derivative of the bottom, all over low, low. Okay, so this fig gif helps us remember the product rule, and this low d high minus high d low all over low, low helps us remember the quotient rule. Okay, again, the sum difference rule is probably not too surprising. Product and quotient rule are surprising, and yet they can be derived using the limit definition of the derivative, for which that proof is well beyond the scope of this boring video. So let's use product and quotient, shall we? Here are a couple examples. Oh, I want to erase that. No, I still want to erase it. So let's assume, and we're just sticking with polynomials for now, let's pretend I want to derive, or if y equals, let's say the product of 6x squared plus 4x minus 1 times 3x plus 2, then what's y prime? Okay, that's another word to say, hey, find the derivative of that product. I got two options here. One, you could expand that and then just use the sum difference rule. I don't want to do that. So now I have another option, and the option is the good old product rule. Okay, I'm recognizing I have to decode that this is the product of two x-containing functions. Therefore, I can differentiate or find the derivative using the product rule. Okay. Now I'm going to write what I'm going to do first. So the product rule says to find the derivative of f times g, I take the derivative of f. So I'm just going to write the derivative of f times plain old g. So that stays for now. Right? There's my g prime, excuse me, f prime eventually, times, that's a times, g. So that's my fig, f prime g. Plus, whoop, now I'm going to take the derivative of g. So I'm just going to write it. I'm not going to take it yet. I'm going to write my intention. 3x plus 2, that's my g prime, times regular old f, which is 6x squared plus 4x minus 1. Okay? So that's my setup, my intention. Now I just have to differentiate, and then I got a little algebra to work through. Okay? So now I'm going to take the derivative of 6x squared. Okay, derivative of 6x squared. 2 comes down, 6 a coefficient. 2 times 6 is 12. X, power goes down 1 to the first. Plus the derivative of 4x. I'm using the sum difference rule, coefficient, power. Plus the derivative of 4x. And you can either use coefficient and power, or the derivative of 3x, derivative of 8x, derivative of 10x, that's linear, is always going to be the coefficient m. Right? So derivative of 4x, the slope of the function y equals 4x, is always 4. Okay, and of course the derivative of 1 is 0. So here's my derivative, 12x plus 4, of the first f piece of this product. Okay? And that gets multiplied by, I'm going to bring that down, regular old g, 3x plus 2. Plus, now I'm going to take the derivative of 3x plus 2. Okay? Now the derivative of 3x, just like the derivative of 4x is 4, the derivative of 3x is 3, using what's called the linear rule, or you can use coefficient, power, plus the derivative of 2, which is 0. Now I'm not even going to write that. We'll just leave it at 3. So here's my g prime. The derivative of 3x plus 2 is 3. Okay, times, and then the regular old second nugget. Okay, and now I got a little cleanup to do. So my calculus is done. So I'm going to take off my calculus hat, take it off, and put on my algebra hat. There's my algebra hat. Okay, because I got to clean up this hot mess, right? And to do so, sometimes we can factor out the greatest common factor. There are two terms. Here's one big one. Here's another one. But these two terms don't have a common factor. So all I'm going to have to do is just expand and then clean up and collect and combine my like terms. So I'm going to expand all this hot mess. Remember, I got to FOIL that. That's 36x squared plus, that ends up being 24x, plus another 12x. That's 24x plus 12x. That's 36x. Plus, and then last time Vlad says it. I just FOILed or expanded that binomial times binomial. Plus, now I'm going to distribute the 3 here, get 18x squared, plus 12x minus 3. Okay, and now I'm just going to collect all my like terms. So, finally, the derivative of y prime is 36x squared plus 18x squared. That's 54 of those x squareds. It's a lot of x squared. Plus 36x plus another 12x. That's 48x. Woo, a lot of those x's. Plus 8 minus 3 is plus 5. Okay? And if I had a little patience, I would see if that factored, which, you know what, I don't have any patience right now, and it doesn't appear to factor after first glance. So I'm going to leave that derivative as it is. Okay? So note, guys, the product rule itself is probably the easy part of this, right? Here's the product rule here, from this step to that step. And then the rest is just a lot of organizing with algebra. Okay? Here's a quotient rule. So again, recall the quotient rule. Low D high minus high D low, all over low low. Okay, you have it written down in your paper somewhere, I hope. Or if you just chat GPT everything. Hopefully not. So anyway, here's a quotient rule problem. Sorry for the snarkiness. What would the derivative of 4x plus 1 over, how about 4x minus 2? Okay, so note that's a quotient, right? I have two functions, an f on top and a g on bottom. There are an x in both of them, so neither are just numbers, which can therefore be expressed as coefficients ultimately. So I got to use a quotient rule. And what the quotient rule says is it's going to be, and I'll write out my intentions, and I remember as low d high, let me find a good pen, low d high minus high d low, all over low low, right? So the quotient rule says, look, if I'm going to derive this quotient, it's going to be low, which is the bottom. So I'll write that in parentheses. D high, so it's a derivative of the top. And I'll just write that. I'm not going to derive yet, write my intentions. Minus high, just the numerator, parentheses. D low times the derivative of the bottom. All over low low, 4x minus 2 squared. Okay? So there's my quotient rule. I set my intention. Now I got to execute. Right? So it's going to be 4x minus 2. That just comes down. Times the derivative of 4x. 4 plus the derivative of 1, 0. So there's my low, d high. Minus high, 4x plus 1. Times, get my ugly mug out of the way, d low, the derivative of 4x minus 2. Again, derivative of 4x is just 4. Minus the derivative of 2, which is 0. All over low low, 4x minus 2 squared. Okay, that's the only calculus step. Okay, now I have to put on my algebra hat. So put on my little algebra hat. Woo, and I got to clean all this hot mess up. And this is a little bit nicer than the last one. And to clean it up, usually I would look to factor something common in the numerator. But I guess a 4 is common. So I could pull a 4 out. Why don't I do that? See what happens. So this term has a 4, the first term. And the second term has a 4 in common. So I'm going to pull out that common factor of 4. This is my algebra hat now. Pull out that 4. Equals 4. Pull that out. And what's left in the first term is 4x minus 2. 4x minus 2 minus what's left when I pull out a 4 in the second term is 4x plus 1. Beep. And I'm not going to expand the bottom because I can tell that, look, x can't be 1/2. Right? That's what we'll later call a point of non-differentiability. But we also can recall that for our original function, that's a point of discontinuity. We'll discuss that later. And then my final step is I'm going to keep the 4 out here. And I'm going to clean up what's inside the parentheses here. So I have a 4x minus 2 minus 4x. So the 4x's cancel. Minus another 1. So I have negative 2 minus 1. Remember that distributes. So 4x minus 2 minus 4x. No more x's. Minus 1. So I get negative 3 on top. And the bottom is still 4x minus 2 squared. So my ultimate answer is negative 12 on top over 4x minus 2, the quantity, squared. So there's my derivative of the original ratio or quotient. Okay, hope you enjoyed this video. I'm sure it was life-changing. See you soon.